Okay, in chapter 12, we learned about discrete random variables and discrete probability models. And we are going to look a little bit more about that and do a little bit of analysis with it. I realize this section had gotten left out of the textbook with its most recent edition. And you have an assignment that it would be very helpful to be familiar with that. So let's start with an example of roulette. This is an American roulette wheel and a betting table that you have there. There is a European version that's a little bit different, that only has the green 0 and doesn't have the green 00 option in there. But the American one has those two options. And so let's look at doing that. If we look at placing a bet, there's all sorts of different ways that you can bet in the roulette wheel. Probably the simplest is if you take your chip and you put it on some sort of money there. So if you put your chip here, you're betting that the number 21 comes out. And let's just do that one for that. You could also put your money down here, you put your chip here in the 13 to 24 range, and if anything between 13 and 24 comes up, you would win. You could bet on red, you could bet on black, you could bet on odd, you can bet on even. You could bet on this column, or you can bet on, the second column, or 1 through 18, or 19 through 36, or, there's all sorts of different ways depending on how you place your money. If you place your money over the corner here, you'll win if any of those four numbers come up. But you don't win as much money as if you bet on a single number. But let's do the single number bet here. And let's say 21, just to do 21 as that in there. And so get my pen back here. What we want to look at is, I'm going to call it R as our random variable. And the outcome of that event is going to be like your winnings is going to be the result of a random variable, a random outcome, wherever that ball gets spun around and lands. Single number bet. And let's just do it. Let's say it's just $1. Say that you're going to bet $1 on that single number bet. And so sort of your the payout for a single number bet is 35 to 1. So if you bet $1 and you win, you'll win $35. And if you bet $10, you'd win $350. And so it's 35 times whatever you bet is the payout. But let's just do $1 to start with. And so if you win, so if you win, you're going to win $35. And if you lose, you're out $1. So you're either up $35, you made a $35 gain, or you're out $1. So those are sort of the two possible options. And then with that random variable, we also want to know the probability that R is equal to whichever one of those values that you're looking at. Whether what's the probability that you win your $35, or what's the probability that you lose your $1. And oops, I want a P there, not a R. I'm P for probability. So let me see if I can try that again here. There. The probability that R equals 35. Well, the probability that your one number comes up, there's a total of 36 numbers, 1 through 36, plus the 00 and the 00. So there's 38 possible options there. And the probability of it landing on the 21 is 1 out of the 38 possibilities. So you've got a 1 in 38 chance of winning the $35. And you've got a 37 out of 38 chance of not winning, of it coming up something other than the 21 that we're betting on, or whatever number that you're choosing to bet on in there. And so there's our probability model. You have 35 happening 1/38 of the time, and -1 happening 37 out of 38 times. And a lot of times what we're interested in is the mean of that probability distribution, mu, or sometimes they'll call it the expected value. Of that thing, or sometimes they'll say exp and then parentheses r. So a random variable is r. It has a value of either -1 or 35, and then you have a probability that each of those occurs. And the mean is found by taking the probability times the outcome. So I'm going to do 35 times 1 out of 38 plus -1 times 37 out of 38. And so you get 35/38 minus 37 out of 38. And so you end up with a -2 out of 38, about -1 out of 19. As a decimal, if you want to look at that as a decimal, it's a minus 0.054, I think. Let me grab my calculator here and check real quick. 2 divided by 38, or minus 0.52. So that in the long run, what this means is that if you were to play roulette lots and lots of times, as a player, you're going to lose about 5 cents out of every dollar that you bet. Every time that you bet a dollar, sometimes you're going to win, sometimes you're going to lose, but more often you're going to lose. But in the long run, that should average out to be 0.052. You're going to lose about 5 cents on every dollar bet that you make in there. And so looking at that mean is useful. It's looking at that house's, and when they say the odds are in the house's favor, if you go to a casino, they always say that the odds are in the house's favor. It's because these expected values are always negative. That means that the person playing is gonna, from their perspective, this is from the person playing, is that on average they're going to lose more money than they bring in. All right. Another example that I have here is the Washington State Lottery. Let's do another example of that and look at that mean. The Washington State Lottery has a daily pick 3. In the daily pick 3, you pick 3 numbers, 0 through 9, and they do a daily drawing, and they tell you kind of what the result of that is. And there's different ways that you can choose to bet your things. Let's look at the straight box option, just because there's 2 different possible outcomes. So your ticket here costs $1, and if the numbers come up, if the numbers come up 357 and you pick 357, you win $290. But if it comes up with the same numbers but they don't match, so you've got 573 or 357, some other combination of the digits 5, 3, and 7, but they don't match the exact order, you win $40. Okay, and so again, that's another random variable. If we look at our winnings from the player's perspective, we can look at that as, so the pick 3, you've got the outcome that you've got, we'll just call it X, I guess, this time, and you're either going to lose $1, you can win $290, or you can win $40. So there's 3 possible outcomes, and we want to know the probability of each of those outcomes. What's the probability that we'll start at the $290? Well, the probability of winning the 290 is 1 in 1,000. If you look at all the possibilities from 000 to 001, 002, all the way up to 999, that's 1,000 different possibilities there that are possible outcomes. And one of those would if you match it perfectly, you've got you win $1,000. And then if we kind of go back and look at the example here, as it gives in it, oops, I went too far. There's the example. That there are 5 other possibilities that you can win the $40 here. So there's a 1 in 1,000 chance that you're going to win the 290. There's a 1 in 5 chance that you're going to win the $40. They put over here that your odds are 1 in 167. That is that you're going to win something. that six. There's 6 out of 1,000 possibilities where you win something, and so that's a 1 in 167 chance of winning something. But we need to be a little bit more specific. We need to look at those 2 different prizes. That there's 5 possibilities out of the 1,000 when you're going to win the $40. And so that means the probability then, these always have to add up to 1, and you're either going to win $290, you're going to win $40, or you're going to lose $1. And so the probability then that you're going to lose $1 is 994 out of 1,000, right? So that adds up to 1,000 if we add across there. So it's 1,000 thousandths. So there's our probability adds to 1 like we need there. So there's 994 times you're going to lose that $1. And so if we look at the expected value of x, or the mean of that probability distribution, the way we calculate it is you take the outcome and you multiply it by the probability. So 99.4% of the time you're going to lose your $1. You're going to win 290 1 out of 1,000 times, and you're going to win $40 5 out of 1,000 times. All right, and so your expected winnings there in the long run would be what, minus 994 plus 290 plus 200 out of 1,000. So 490 would be the positive ones, and 994 minus 490. So I'm looking at a negative 504 out of 1,000, which as a decimal would be 0.504. So on average, in the long run, you're giving, if you played this a lot of times, the average return would be 50 cents. Well, you'd lose 50 cents every time you'd bet $1. So if you want your money to last longer, go to the casino and play roulette. You're only losing 5 cents every time you place a bet. Paying the pick 3, you're losing 50 cents every time you place a bet. On average, in the long run, that's going to work out. Assuming that you win occasionally, that's gonna do it. I mean, you're gonna win $290 for your $1, but that doesn't happen very often. Only 1 in 1,000 times in there. Whereas with roulette, 1 out of 38, that's considerably more likely. I mean, it still doesn't happen very often, but it's more likely than 1 out of 1,000 in there. So you're more likely to win that $35 playing roulette. That's you play 1,000 times. What's 1,000 times 38? You play 1,000 times 38. 1,000 divided by 38, I mean. So you play 1,000 times, you'd expect to win about 26 times, roughly speaking, in those 1,000 plays, whereas you'd only expect to win once with the pick 3. But with the pick 3, you win a whole lot more money than you do winning when you win roulette. So, it's a gamble, but the odds are in the state's favor in this case. So buy those lottery tickets. Keep paying taxes. I appreciate you doing that, volunteering to pay taxes like that. All right. Another example are Pokemon cards. You may not know this, but I'm also not just a math professor. I'm also a Pokemon professor, and the Pokemon trading card game. And a lot of attacks will have something. Well, a fair number of attacks have something that involve a flip of a coin, like this Fury Cutter attack that Scyther has. It says flip 4 coins. The attack does 10 damage plus 10 more damage if exactly 1 comes up heads, 20 more damage if exactly 2 are heads, 40 more damage if exactly 3 are heads, or 80 more damage if all 4 are heads. And so if we look for that random variable, the amount of damage that you do is a random variable. You can do 10 damage. The possibilities are 10 damage. If all of them are tails, you do 10 damage. If 1 is heads, you'll do 20 damage. If 2 are exactly heads, you're going to do 20 damage, 20 more damage plus the 10 damage, so 30 damage. If 3 are heads, you're going to do 40 plus the 10, so you're going to do 50 damage, and you're going to do 90 damage if all 4 coins are heads. But then we need to work out what are the probabilities that you can come up with there on that, and that takes a little bit more work. I guess your options are, maybe we could just list it out. Heads, 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 heads. We could get all heads. Heads, 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 tails. Let's try to be very systematic about this. If I'm looking at combinations with just 1 tails in it, I could get that tails on the last flip, the second to the last flip, or the first flip. And those are all the possibilities that I have with exactly one tails in them. If I look at maybe 2 tails, what if I do tails, tails, heads, heads, tails, heads, tails, heads, tails. Come on, what happened to my pen? Why'd you stop writing? Tails, heads, heads, tails. So I move that T through that diagonal all the way across, and I think that's every place I can put it. So let's start with the heads, tails, tails, heads, heads, tails, heads, tails. Let's see, that's all the positions where that tails is in this, where I start with the heads and then go to a tails. I think those are all the possibilities I could come up with. I could do heads, heads, tails, tails. Okay. Yep, and then I think is that it with 2? What if I started with 2 tails? I think that's it. Is that all of them? Started with 2 tails and I finished with 2 heads. And then you want to double check, kind of make sure that you've got every sort of possibility there. I think that's it. Okay. And then you can do a thing where you can do tails, 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 3 tails, and then a heads. And then a tails, tails, heads, tails. This one's a little bit easier because you've got that head sort of progressing through your tails sort of thing option there. And then you've got your all tails as your final option. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possibilities. And in this situation, I'm only doing 10 damage. So there's 1 out of 16 chances that I'm doing 10 damage. These are the ones where you're getting 1 heads, and there's 1, 2, 3, 4 of them. So there's a 4 out of 16 chance of doing 20 damage. 1, 2, 3, 4, 5, 6 possibilities. 6 out of 16 chance that you're going to get exactly 2 heads and do 30 damage. There are another 4 options here where you're going to do 50 damage. And then there's that one rare option where all 4 are heads and you do 90 damage in there. So there's a nice discrete probability model, nice random variable where you got different numbers that can come up, the amount of damage your attack does, and then we got a probability associated with each one of those. So there's that. And we can also compute the mean of that probability distribution. We could look at our expected value for f. And the way you do it is you take the numerical value and multiply it by the probability that that thing happens. So 10 times 1/16 plus 20 times 4/16 plus 30 times 6/16 plus 50 times 4/16 plus 90 times 1/16. And that will give you your expected value. The nice thing is the denominator is 16 all the way across. And if we figure out the numerators and add them up, I'm going to have 10/16. I'm going to have 80/16. 3 times 6 is 180, or 30 times 6 is 180 sixteenths there. And then 5 times 40 is 200 sixteenths, and then a 90. And I get 560 over 16. So if I divide that out, I get 35. So on average, if you were to use this Fury cutter attack, on average in the long run, if you do it a lot of times, you'll do on average a 35 damage per turn on average from that attack. So that's your expected value. Your average sort of return is 35 damage in the case of this Pokemon card here of doing that damage. All right, so that's the expected value of a discrete probability function. It's pretty straightforward. You just take the, you're looking at some sort of numerical amount, and then you multiply it by the probability of that amount. And you do that for every single one, and then add them all up, and it will tell you your expected value, which is the mean, which is kind of the average result. If you were to do that thing a whole bunch of times, on average, that's what's going to happen in the long run. Okay? All right.